projects. In this video, we are going to explain about the project title Sleep Apnea Detection from Single-Lead ECG, a comprehensive analysis of machine learning and deep learning algorithms. The project Sleep Apnea Detection from Single-Lead ECG is an essential healthcare response to the urgent problem of sleep apnea. Sleep apnea is a potentially serious sleep disorder in which breathing repeatedly stops and starts. It accurately detects this condition from single-lead ECG data utilizing a wide range of machine learning and deep learning methods, such as inception, V3, and stacking regression. A timely diagnosis is essential for better patient outcomes. Users can provide feature data or ECG images which are processed by a trained model. The data are presented in the project's front end, making them accessible and possibly transformational in improving early sleep apnea detection and improving public health. The project uses a wide variety of machine learning and deep learning techniques to produce a comprehensive solution for sleep apnea detection using single-lead ECG data. These algorithms, which also process and examine feature values and ECG images, include inception, V3, VGG16, LSTM, and others. They are crucial in correctly diagnosing sleep apnea and allowing for an early diagnosis. They are significant since the combination of inception, V3 for image data and a voting regressor for feature data has demonstrated improved accuracy. The project uses Flask with SQLite for user interaction, allowing users to input either picture or feature data, pre-processing it for prediction and presenting the results through an intuitive front end. Requirements. The requirements of the project are hardware requirements and software requirements. In hardware requirements, we have operating system of Windows, processor of i5 and above, RAM of 8GB and above, hard disk of 25GB and above. Software requirements. In software requirements, we have Anaconda 3 and Visual Studio Community version. Flow of work. To implement this project, we have designed the following modules. The first module is importing the packages. In this module, the necessary Python libraries and packages are imported. These libraries include data manipulation tools like NumPy and Pandas, machine learning frameworks such as scikit-learn and TensorFlow or Keras for deep learning, and data visualization libraries like Matplotlib and Seaborn. Exploring the dataset. This step involves gaining a comprehensive understanding of the dataset. Exploratory data analysis (EDA) techniques are used to examine the data's characteristics, including its size, structure, and content. It helps identify any missing values, outliers, or patterns within the data. Data processing. Data pre-processing is a crucial phase that involves cleaning and transforming the dataset to make it suitable for machine learning models. Tasks may include handling missing values, encoding categorical variables, scaling numerical features, and feature engineering to create relevant attributes. Visualization using Seaborn and Matplotlib. Data visualization is essential for understanding the data's distribution, relationships, and trends. Seaborn and Matplotlib are used to create graphical representations such as histograms, scatter plots, and heat maps, which aid in making data-driven decisions during model development. Splitting the data to train and test. To evaluate the performance of machine learning and deep learning models, the dataset is divided into two subsets, a training set and a testing set. The training set is used to train the models, while the testing set assesses their performance on unseen data. Common split ratios are 70/30 or 80/20. Building the model. This is the core of the project where various machine learning and deep learning algorithms are implemented to detect sleep apnea. The choice of algorithms, hyperparameters tuning, and model architectures, example neural network layers, are crucial in this phase. So the deep learning algorithms are inception V3. Inception V3 is a deep convolutional neural network CNN architecture designed for image classification tasks. It's known for its efficiency in training deep networks while using fewer parameters. In the context of this project, Inception V3 may be applied to analyze ECG images and extract relevant features for sleep apnea detection. VGG16 and VGG19. VGG16 and VGG19 are famous CNN architectures characterized by their deep network structures with a series of convolutional and max pooling layers. They excel at feature extraction from images. In this project, VGG16 and VGG19 can be utilized to analyze ECG images and identify patterns related to sleep apnea. MobileNet. MobileNet is a lightweight CNN architecture specially designed for mobile and embedded devices. It's known for its efficiency and low computational requirements. MobileNet may be used in this project to analyze ECG images with a focus on resource-constructed environments. ZFNet. ZFNet is another CNN architecture that has been used for image classification tasks. It features a deep network with a smaller number of parameters compared to some other architectures, making it suitable for certain applications within limited resources. AlexNet. AlexNet is a pioneering CNN architecture known for its breakthrough in image classification tasks. It employs multiple convolutional and pooling layers and can be used for image feature extraction, including ECG images. LSTM with exception. This refers to a combination of long short-term memory LSTM networks with the exception architecture. LSTM is a type of recurrent neural network RNN known for handling sequential data. In this case, it could be used with the exception architecture to analyze sequential ECG data for sleep apnea detection. BiLSTM. Bidirectional LSTM. BiLSTM is a variant of LSTM that processes data in both forward and backward directions. This is particularly useful for capturing bidirectional dependencies in sequential data. It can be applied to analyze ECG data for sleep apnea detection. GRU. Gated Recurrent Unit. GRU is another type of recurrent neural network similar to LSTM but with a simplified structure. It can also be used to process sequential ECG data and capture patterns related to sleep apnea. And these are the hybrid models, which include hybrid ZFNet plus LSTM, hybrid ZFNet plus BiLSTM, hybrid ZFNet plus GRU, and hybrid AlexNet plus LSTM. The hybrid models mentioned in the project combine deep learning architectures with recurrent neural network. These combinations aim to leverage both the strength of CNNs in image feature extraction and the sequential data processing capabilities of RNN to improve sleep apnea detection. Machine learning algorithms. These are the machine learning algorithms used in this project. Linear regression. Linear regression is a simple and widely used supervised learning algorithm for regression tasks. It models the relationship between a dependent variable, in this case sleep apnea prediction, and one or more independent variables, features from ECG data using a linear equation. It can provide insights into how different features correlate with sleep apnea. Random forest. Random forest is an ensemble learning method that consists of multiple decision trees. It's particularly useful for both classification and regression tasks. In this project, it can be applied to analyze feature data from ECG signals and make predictions about sleep apnea. ElasticNet. ElasticNet is a regression algorithm that combines the properties of both L1 lasso and L2 ridge regularization. It's used when there are many features and it helps prevent overfitting. It can be used to analyze feature data for sleep apnea prediction. Decision tree. Decision trees are used for both classification and regression tasks. They represent decisions and their possible consequences in a tree-like structure. Decision trees can be employed to model the relationship between ECG data features and sleep apnea. Navy Bayes. Navy Bayes is a probabilistic classification algorithm that makes predictions based on Bayes' theorem. It's particularly effective for text classification but can be adapted for other tasks. In this project, it is used to classify or predict sleep apnea based on ECG data. Gaussian process. Gaussian process is a probabilistic model that can be used for regression and classification tasks. It models the distribution of data points as Gaussian distributions. In the context of sleep apnea detection, it can capture uncertainties and make probabilistic predictions. Support vector machine. SVM is a powerful classification algorithm that finds a hyperplane to separate different classes. It can be used for binary classification problems such as predicting the presence or absence of sleep apnea based on ECG features. KNN, K nearest neighbor. KNN is a simple yet effective algorithm for classification and regression tasks. It predicts the class or value of a data point based on the majority, class, or average of its nearest neighbors. It can can be used to classify sleep apnea cases based on ECG data. AdaBoost Regressor. AdaBoost is an ensemble learning technique that combines multiple weak learners, that is decision tree, to create a strong learner. It's often used for regression tasks and may be applied to improve sleep apnea detection accuracy. MLP, multi-layer perceptron. MLP is a type of artificial neural network with multiple layers of interconnected nodes. It's a versatile model that can be used for various machine learning tasks, including sleep apnea detection from ECG data. Gradient boosting. Gradient boosting is an ensemble learning technique that builds a strong learner by sequentially adding weak learners. It's widely used for regression and classification tasks and can be applied to enhance the accuracy of sleep apnea prediction. Stacking regressor. Stacking is an ensemble learning method that combines the predictions of multiple base models to create a final predictor. It's employed to improve the predictive performance and robustness of sleep apnea detection models. Voting regressor or majority rule. Voting regressor is an ensemble method that combines the predictions of multiple regression models by averaging or taking the majority vote. It helps in aggregating predictions from different models to improve accuracy. LDA, Linear Discriminant Analysis. LDA is a dimensionality reduction and classification technique. It seeks to find linear combinations of features that best separate classes. LDA can be used for feature selection or classification tasks in sleep apnea detection. Quadratic Discriminant Analysis QDA. QDA is a generalization of LDA that allows for different covariance matrices for each class. It's used when the assumption of equal covariance matrices in LDA is not met. QDA can be applied to complex data distributions in sleep apnea prediction. Training the model. This module involves training the selected machine learning or deep learning models using the prepared dataset. It includes feeding the model with labeled data, features in corresponding sleep apnea labels, and adjusting the model's internal parameters, weights and biases through an optimization process to minimize prediction errors. Training is a crucial step as it enables the model to learn patterns and relationships within the data, allowing it to make accurate predictions. Building the model with Inception v3 for image data. Inception v3 is chosen as the deep learning model for processing image data, especially the ECG images. Inception v3 is a convolutional neural network CNN architecture that excels in feature extraction from images. This module involves configuring, training, and fine-tuning Inception v3 for the task of identifying sleep apnea from ECG images. The model learns to recognize specific patterns and features in these images that are indicative of sleep apnea. Voting regressor for feature data. For feature data, a voting regressor is selected as a machine learning model. The voting regressor combines the predictions of multiple machine learning models, that is random forest linear regression, and takes an ensemble approach to improve accuracy. In this context, it aggregates predictions made by different models, harnessing their collective wisdom to provide a more accurate prediction of sleep apnea based on feature data extracted from ECG signals. Flask framework with SQLite for sign up and sign in. Flask is a microweb framework for Python used to create web applications. In this module, Flask is employed to build a user interface for the project. Users can sign up and sign in to access the system securely. SQLite, a lightweight relational database management system, is used to manage user data, ensuring user registration and authentication functionalities. User input has image or feature values. This part of the project allows users to input data for sleep apnea prediction. Users have the flexibility to input either ECG images or feature values, making the system versatile and accommodating to different user preferences and data sources. Pre-processing user input for prediction. Once user input is received, it undergoes pre-processing to ensure it's in the correct format and aligns with the model's expectations. For images, this might involve resizing, normalization, and formatting. For feature values, it might involve data scaling and validation to ensure the input data is suitable for the model's prediction. Using the trained model for prediction. After pre-processing, the user's input data is fed into the trained models. The Inception V3 model processes image data, while the voting regressor handles feature data. These models apply their learned knowledge to the user's input, making predictions about sleep apnea based on the provided data, displaying the final outcome through front end. The results of the prediction, whether it's a classification, presence or absence of sleep apnea, or a regression, quantitative prediction, are presented to the user through a user-friendly front-end interface. This can include visualizations, text-based results, or other informative feedback, making the system accessible and interpretable for users. Execution. To execute this project, first we need to open the code folder which contains the project source code files. This is the code folder. This is the static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap files. This is the template folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represent different pages of the website. This is app.py file. This .py file contains the information related to front-end logic. It could include code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. These are the model files. These are model files which contain algorithm information which will be loaded in the project code during runtime. This is signup.db file. This file is the database file used to store user information. This is ipynb file. This is a Jupyter Notebook file which contains a combination of code, graphs, and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for data science. First, we need to copy the path of the code folder from the address bar of the file explorer. I'm copying the path. Open the Anaconda prompt. Use the cd command followed by a space and then paste the copied path. And hit enter. This command is used to change the current directory to the code folder's path. Compile the app.py file using the command python space app.py. I'm typing python space app.py and hit enter. This command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address and port. Copy the local link. I'm copying the link. And paste it into any web browser. I usually prefer Google Chrome and hit enter. The homepage of the project is displayed in the browser. This is the front end built using Flask framework. So here, this is the homepage of the project. Click on sign up. If we are a new user, we need to register first. But I have already registered, so click on sign in. Enter the username and the password. And submit. This is the homepage of the project. So we need to enter these parameters to predict AHI, that is apnea hyponia index. So I'm entering all these details. So here I have entered all the details, that is male, value of the BQ, value of ESS, value of BMI, weight, height, value of head, value of neck, value of waist, value of buttock, and the age. Now click on submit to predict the AHI, that is apnea hypopnea index, and the type of the sleep apnea. So here we can see the outcome is predicted value of AHI is 29.658 events per hour, and it is predicted as moderate OSA. OSA is obstructive sleep apnea. So this is moderate obstructive sleep apnea. Now we will enter more details. So let us enter these details again to predict the AHI. So here I have entered the details as female, the value of PQ, value of ES, value of BMI, weight, height, value of head, value of neck, value of face, and value of buttock, and the age. Now click on submit. So here we can see the outcome is predicted value of AHI is 40.766 events per hour, and it is predicted as severe OSA, that is severe obstructive sleep apnea. Now let us enter the values again. So here I have entered the details as male, and I have entered the value of PQ as 0, ES is 6, BMI 19.27, weight 57, height 172, value of head as 58, value of neck as 34, value of face 72, value of buttock 86, and the age as 21. Now click on submit. So the outcome we got is predicted value of AHI is 1.619 events per hour, and the type of sleep apnea here is mild OSA, that is mild obstructive sleep apnea. So in this way, by entering these parameters, we can predict the type of sleep apnea, whether it is mild, moderate, or severe OSA, that is obstructive sleep apnea. Now click on ECG image. So here we need to upload the image, and the type of the sleep apnea will be predicted. Now let us choose the file. Open. Click on upload. So here we can see this is the uploaded image, and for the given input image, the sleep apnea is F, that is fusion of ventricular and normal beat. Now let us upload one more image and check the type of the sleep apnea. So here we can see this is the uploaded image, and the given input image, the sleep apnea is fusion of ventricular and normal beat. Let us upload one more image. And open, upload. So this is the uploaded image, and the given input image, the sleep apnea is fusion of ventricular and normal beat. Let us upload one more image. So here this is the uploaded image, and the given input image, the sleep apnea is fusion of ventricular and normal beat. Let us upload one more image. So this is the uploaded image, and the result is the sleep apnea is fusion of ventricular and normal beat. In this way, by uploading the image, we can predict the type of the sleep apnea. Now click on sign out, and the conclusion of the project is the project shows how different machine learning and deep learning models can accurately identify sleep apnea from single-lead ECG data. To get the dataset ready for analysis, extensive exploration, data processing, and visualization were carried out. The combination of inception V3 for image data and a voting regressor for feature data among the studied algorithms proved to be the most accurate method. Accessibility is improved by using Flash with SQLite for user interaction. Users can provide feature values or ECG images, and the trained model will deliver accurate predictions. In addition to potentially improving healthcare outcomes, this effort shows the significance of algorithmic approaches in medical diagnostics and hold promise for early sleep apnea identification.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.